Welcome back, guys. So today we are going to discuss a very important topic, and that is basically the today we are going to discuss NAND and NOR equivalent of the fundamental digital logic gates or digital logic circuits. So why is it important to represent them with these NAND and NOR gates? This is because the availability of NAND and NOR gate as a natural gates. Okay, so therefore most of the gates, either it is NOT gate, AND gate or OR gate, or most of them are basically made of the NAND and NOR gate, and that is the easy availability of the NAND and NOR gates. Okay, so first of all, what we are going to do, we are going to discuss the NAND gate. Okay, and we have to see that how different gates can be made up of this NAND gate. Okay, so the first gate here, let me see that if I have a NAND gate, so NAND gate is basically represented by the symbol which is here, and we are going to discuss a NAND gate which has two inputs. Okay, so if we have two input NAND gate and at the input we apply A such that the two inputs are shorted together, so at the output of it, what I will get A complement, and that is basically the equivalent of a gate which is called the inverter or NOT gate, to which we apply the input and the output we get the inverting output. Okay, so this is the NOT gate which is made of this. So let me write the name of it. So this is the NOT gate which is made of this NAND gate. Okay, similarly if we have a NAND gate, okay, let me write it. If we have a NAND gate and if I apply two inputs to it, what I will get out of it, I will get AB whole complement. Okay, so if the same output is applied to another gate which is another NAND gate, okay, so if the two input NAND gates we short it down and to it we apply it, what I will get at the output of it, I will get here AB, okay, which is which we can very easily see that this is a simplified version of a gate which is called the AND gate. Okay, so at the input of it I have applied AB, and at the output of it what I have got AB. Okay, so we can very easily see here that two of the most fundamental gates, one is the, let me underline them. So the first of them is the NOT gate, second is the AND gate. We can very easily make them by using the NAND gates. Okay, similarly if I have, let me use it here, and if I have two AND gates, okay, this is a first AND gate, this is a second NAND gate. Okay, so if I have two NAND gates and to them I have applied what, to this gate I have applied A, while to this I have applied B, and at the output of them what I will get here, I will get A complement, while here I have got this B complement, and these are again applied to another NAND gate, and if this is connected here, okay, and at the output of it what I will get, at the output of it I will get A complement dot B complement and whole complement. Okay, so what is this? This is basically the expression here, and if I want to simplify it, let me simplify it by using this blue color. So according to the De Morgan's law, I know that A complement dot B complement whole complement is equal to what? That is equal to the A complement plus B complement. What is this? This is because this sign has been changed while the complement has been issued to both of the terms here. So what I will get here, complement and complement will cancel each other. We can see that this will cancel each other, while here this symbol has been changed to this. So at the output of it, what I will get? I will get here a plus b. So therefore I can write here that this is equal to the a plus b, which is what, which I can very easily see that the functionality of the OR gate to which two inputs A and B are applied, and the output of it I have got this A plus B, and this is the functionality of the OR gate. Okay. So what if I want to make it a NOR gate? What I can do here, I can very easily connect here the inverter or NOT gate, and this inverter is here, this one is the inverter, and I can use it here, and to that I will get what? I will get here then this gate, okay, and that would be the NOR gate to which the two inputs are applied, and at the output of it, what I will get? I will get a plus b whole complement. Okay. So these are all the gates. Okay, this is the gate number 1, 2 and 3. So these are the fundamental gates which are made up of this NAND gate. Okay. So this is a one of the very important lecture in which we have seen that how different gates can be made up of this NAND gate. Okay. In the next lecture we will talk about the gates which can be made of this NOR gate. So stay tuned, and I will see you in the next lecture with the next topic. Okay. See you soon. Welcome back, guys. So this is the glimpse of the previous lecture in which we have seen all the fundamental gates, which included NOT gate, AND gate and OR gate, and similarly we have seen that how to make the NOR gate out of the NAND gates. Okay, so these are all the gates which are made up of this NAND gate, and this is because of the universality or universal property of the NAND gate. Okay, so today we are going to see the same gates which I can make by using this NOR gate. So let me start it in the second sheet here. So NOR equivalent. Okay, so what I have to do here, let me use the same NOR gate. Okay, and we can very easily see that the NOR gate can be represented by this OR with the bubble at the output end, and what I will get here, this is what, this is AB, and the output of it is A plus B whole complement. Okay, so let me see the equivalent of them, and I can see that initially once I will have this NOR gate, okay, and at the input we have two inputs, and when these are combined together, shorted with each other, and we apply an input, what I will get at the output of it, I will get here a complement, and we can very easily see that this is the functionality of a very fundamental gate, that is the inverter or NOT gate to which I applied this A, and at the output of which I get this A complement, and this is what, this is the NOT gate. Okay, similarly if I have a gate which is the NOR gate here, and at the input of it I have applied A and B, which are two inputs. So at the output of it, what I will get, I will get A plus B whole complement, and then this is applied to the another gate, this is another NOR gate, and the two inputs of them are shorted together, and the same output of the first gate is applied to the input of this. What I will get at the output of it, the complement of the both will be cancelled with each other because negative of the negative is positive. So at the output of it, I will get A plus B, which is basically what, the same gate which I can see here, that the same property to which two inputs are applied, and the at the output of them I will get A plus B, and this is what, this is the OR gate. Okay, so two very fundamental gates, the NOT gate and OR gate, are made up of these NOR gates. So these are the NOR equivalents of the fundamental gates. In third part of it, I will have, let me have two NOR gates. This is a first NOR gate. Let me have another NOR gate. To these we have the inputs. Okay, let me short them down. So at the first I have A, at the second I have B. Okay, so at the output of first I will get A complement, at the output of second I have got this B complement. Okay, the same is applied to the third gate, which is a NOR gate and which has two inputs. These are applied here, okay, at the output of them, and at the output of them what I will get here, I will get A complement plus B complement and whole complement. Okay, so let me simplify them as I have previously done. So by using the De Morgan's law, what I can get from it is that it will be A complement plus B complement, and this is the whole complement of it. So what I will get here, so at it I will get A complement dot B complement, and what is this? I can very easily see that this plus has been changed to this multiplication, and this whole complement has been given to both of them, and the complement of the complement is positive. So therefore I will get here AB. Okay, similarly here I can write that at the output of it I will get AB. Okay, so this is what this is the AND property, and I can see here that this is the same property which a very fundamental gate possess, and that gate is called the AND gate. Okay, so if I want to make it a NAND gate, what I have to do, I have to make or insert the inverter here. So in order to insert the inverter, let me use this red color for it. So I will have to insert another NOR gate here, and at the output of it what I will get, I will get a B complement. So this will be what, let me use this color. So this will, in this insertion with this AND gate will give me another gate, and that would be the NAND gate. Okay, so the functionalities of the four gates are now mentioned in this lecture, in which we can very easily see that all of these gates are made up of a very simplified gate, and that is basically the NOR gate. Okay, so these are the NOR equivalent of the gates. So the first one here is the NOT gate, second one is the OR gate, and the third one is the AND gate, while the last one is the NAND gate. Okay, so that's it for today, in which previously we have seen the equivalents of the basic or fundamental logic gates, and we have composed all of them by using the, we have developed all of them by using the NAND gate because of the universality of the NAND gate. Similarly, in today's lecture we have talked about the universal property of the NOR gate, that I can create any circuit or any logic gate by using the NOR gate. So that's it for today, and from the next lecture we will try to solve the related questions which are in our exercise, and we will see that how the equivalent circuits are helpful for us in constructing different logic gates. So I hope it's enough for today, and I will see you with some more interesting questions in our upcoming video. Till then, take care of yourself.